Thin layer chromatography, performing an analysis. In this webcast, we will discuss how a TLC analysis is performed. We will talk about how to set up and then use or develop a TLC plate, how to view or visualize that TLC plate, and then how to analyze and interpret a TLC plate. First, you have to prepare your TLC plate. Step 1 is to acquire your TLC plate, and then draw a line a short distance away from the bottom of the plate, somewhere around 1 centimeter. You don't have to actually measure 1 centimeter, just eyeball it. It is important to draw this line in pencil. Pen ink contains many different organic compounds. Those organic compounds will contaminate your TLC experiment. Every time you draw on a TLC plate, you must use pencil. Now that we have drawn this horizontal line across our TLC plate, we will add hash marks perpendicular to that line. The number of hash marks you draw will depend on the number of samples you intend to place onto your TLC plate. Sometimes, one of these hashes will be designated a reference hash. Each of these hashes corresponds to what organic chemists will call a lane. The compounds will move from the bottom of this TLC plate to the top in a straight line. So each hash mark corresponds to a particular lane on the TLC plate. The purpose of a reference lane is to provide something to compare to once the experiment is complete. Once you have made your hash marks and labeled your hash marks, you will then spot a solution of your compound. For this experiment, the solutions will be made for you. You will take a small glass capillary and draw a small amount of the solution into the glass capillary. You will then spot a small amount of those solutions onto each hash mark. It is important to try and keep the spots small. Spots that are too large will not elute properly. After you spot your samples, your TLC will look wet. You will then wait until the spots have completely dried and all the solvent has evaporated. You can accelerate this process by carefully drying your TLC plate using an airstream. Now that your TLC plate is prepared, the time has come to do what we call developing the plate. It is time to perform our TLC experiment. First, you will take a container, in your case you will take a beaker, and you will add a small amount of your eluent to your beaker. Do not measure half a centimeter, simply eyeball it. Once your solvent is in your beaker, you will then add your TLC plate to your beaker using a pair of tweezers. You will then cover your beaker using aluminum foil. In your case, you are also instructed to add a filter paper to your beaker prior to placing your TLC plate into the beaker. The purpose of the filter paper is to evaporate some of the solvent. What this does is this saturates the atmosphere in the beaker with evaporated solvent. This will slow down the evaporation of the eluent as it travels up the TLC plate, allowing for faster development. When placing your TLC plate into the eluent, do ensure that your horizontal line is above the solvent. If your horizontal line is submerged in the solvent, your analytes will simply dissolve and will not travel up the plate. Now that your TLC plate is in the solvent, capillary action will draw the eluent up your TLC plate. You will simply wait until the eluent is about 1 centimeter from the top of the plate. This may take a few minutes. You can accelerate this process by using filter paper as instructed in the lab manual, as well as ensuring that you have completely covered the top of your beaker. The end of the development process should look something like this, where your eluent is about 1 centimeter from the top of your TLC plate. This line of solvent is what we call the solvent front. The solvent front is the maximum distance the solvent has traveled from the bottom of the plate to the top of the plate. Once your solvent front has traveled an appropriate distance, you will then remove your plate from the beaker using tweezers. You must then immediately mark the solvent front with your pencil. Once you remove the TLC plate from the beaker, your solvent will begin evaporating immediately. Do not wait too long to mark the solvent front, otherwise the solvent will completely evaporate and you will have no idea where to make your mark. After marking the solvent front, simply wait for your TLC plate to dry. You can accelerate this process by carefully drying it with an airstream. After developing your TLC plate and allowing it to dry, your TLC plate will likely look something very similar to this, the same as when it started. Don't be fooled. Just because you cannot see any compounds, it does not mean that no compounds are here. After your TLC plate has dried, the first thing you will do is circle any visible spots on the TLC plate with the pencil. However, most organic compounds are not colored. Therefore, they will be invisible to the naked eye on a TLC plate. If most compounds are invisible to your eye, how can you see them? This is where a process called visualization comes in handy. Visualization is the term for techniques that we use in order to visualize or see the compounds on our TLC plate. The first type of visualization you will use is ultraviolet light. You will take your TLC plate and place it under an ultraviolet lamp, which will be located in the labs. After placing the TLC plate under the UV light, your TLC plate will glow green, with the exception of these dark spots. Now, these dark spots you see correspond to different compounds. Each spot is one compound. Now that you can see these spots, you will mark them following the instructions in your lab manual. The reason that we can use UV light in this way is because TLC plates are often doped with an indicator, such as zinc sulfide. These indicators fluoresce green under the type of ultraviolet light you will be using. Compounds on the TLC plate will block this fluorescence from occurring and will therefore appear dark. You will also be visualizing your TLC plate using iodine. How this technique works is you will take your TLC plate and you will place it into a jar that contains iodine. The iodine in the chamber will sublime and will stick to the surface of the TLC plate, turning it a brown color. As the TLC plate turns color, you will notice the appearance of several dark spots. Once you are confident that all spots have been visualized, usually waiting long enough for the entire plate to turn brown is enough, you will then remove the plate and mark the spots according to the instructions in your lab manual. Don't wait too long, however. Remember, iodine sublimes. The moment you remove your TLC plate from the iodine chamber, the iodine on your TLC plate will begin to sublime into the atmosphere and disappear. Remember to quickly mark your spots before all of your iodine disappears. Why are we using two visualizing methods? On the previous slide, I showed you this TLC plate, which was visualized using iodine. Some of you may have noticed that this TLC plate showed different spots than the TLC plate visualized using ultraviolet light. That wasn't by accident. Not all compounds can be visualized using all methods. If we look at the plate visualized using ultraviolet light, we see these bottom spots that are not present on the TLC plate visualized using iodine. At the top of the iodine plate, we see these two spots that are not present on the TLC plate visualized using ultraviolet light. This is why it is important to have different methods of visualization. In the TLC experiment, you may find some compounds that can be visualized using one method, but not by the other. Okay, so we've developed a TLC plate, we have visualized it, and we have labeled the various spots on our TLC plate. What do we actually record in our notebook? You usually record a few things. One is a sketch of the TLC plate, and the second is a calculation of what is called a retention factor. A retention factor is a measure of the distance a compound travels across a TLC plate. The calculation is actually quite simple. To calculate the retention factor, or RF, you take the distance your analyte traveled and divide it by the distance the eluent traveled. In other words, it's the distance a spot traveled over the distance the solvent front traveled. Let us look at this TLC plate for an example. I want to measure the retention factor of the purple spot. To calculate that, I have to find the distance the purple spot traveled, which in this case is 3.5 centimeters. To find this value, I measure the distance from where the spot started, where I placed it, to where the spot ended, up here. And I measure at the middle of the spot. I then take this value and divide it by the distance the solvent front traveled, which is the distance from the horizontal line to the mark I made to indicate the solvent front. I plug these values into this equation, 3.5 over 6 to get a value of 0.58. Notice that the retention factor is unitless. This is because the retention factor is simply a ratio of distances. That being said, when performing your calculation, do not forget to include your units. Recording this data is important because the retention factor of a compound is characteristic of that compound. What do I mean by characteristic? What that means is that if I repeat this TLC experiment again and again and again, the retention factor for the purple spot will always be 0.58. However, there are important criteria to meet first. The retention factor for a compound is constant only in the exact chromatographic conditions. This means that if I change the stationary phase, I change the retention factor. If I change the mobile phase, I change the retention factor. This is why it is important to always record the exact TLC conditions you use. Now, some quick tips to help you perform the TLC experiment. First, make sure you are always wearing your gloves and do not touch the silica gel with your bare hands. If you touch a TLC plate with your bare hands, the oils on your hand will contaminate your experiment. When drawing your lines, don't push down too hard. The silica gel layer on the TLC plates is, as the name of the technique suggests, a very thin layer and is easy to break through. Draw lightly and carefully on a TLC plate to not damage it. When spotting your solutions, try to spot small spots of roughly equal size. Using small spots helps ensure that you have high-quality TLC plates. Keep a careful eye on the TLC plate as you are developing it. Do not allow the solvent front to reach the top of the TLC plate. This is what we call overdeveloping. Overdeveloping a TLC plate means that your retention factors are no longer reliable. When visualizing your TLC plates using ultraviolet light, do be careful to not expose your eyes or your skin to the UV light. The iodine in the iodine chambers is corrosive and toxic, so please use it carefully and only in the fume hood. And finally, this is your first wet experiment. That means this will be the first time you'll have to dispose of various chemicals and used equipment. Make sure you dispose of waste in the appropriate containers. That brings us to the end of this webcast. To recap, visualization is the process used to allow compounds on a TLC plate to be seen. Different methods of visualization will work for different compounds. As discussed in this webcast, you will be using two methods of visualization in the experiment, one using ultraviolet light and one using iodine. The retention factor of a compound is a measure of the distance a compound travels compared to the distance the solvent front travels. This value is characteristic of a particular compound. This comes with a caveat, however, it is characteristic only if all aspects of a particular TLC experiment are constant. For example, if you change the stationary phase, you change the retention factor. If you change the mobile phase, you change the retention factor.